All right, so today is crystal field theory. That's our topic. This is talking about the electrons and the d orbitals, and so the electrons and the d orbitals are a little different than what we're used to seeing in reference to the s and the p's. You say, well, how do you figure? Well, it's because of how the electrons interact with each other. So you know that there's 10 valence electrons and that are total in the transition metals, and that's a high number of electrons to put right next to each other. Sometimes the orbitals themselves have to alter to allow for stability of the atom in this electron cloud. So again, so bonds are formed due to the attraction of the electrons on the ligand for the charge on the metal ion cation. We talked about the complex the other day, and complexes, are highly favored to begin with. But what's important is the metal is that attraction where all the ligands attached to it. And keep in mind that we talked about, coordination numbers 6 and 4 being the most common, and we'll see that show up here in the crystal field theory. Now, the other thing you have to keep in mind that the electrons and the ligands repel electrons and the unhybridized d orbitals. Keep in mind, we did talk about hybridization in 151, and with hybridization, I'm just going to draw you like a quick little blip here. So if we take carbon, all right, so carbon has 4 valence electrons, 1, 2, 3, 4. This is your S and this is your P. And so when we talk about bonding, we always draw 4 bonds to carbon. Now, what you have to observe here is the fact that when you look, there are only 2 places where the electrons can bond, share, and that's right here and here. This is in the original electron configuration. This is unhybridized. So as we talk about hybridization, what has to happen is the electrons arrange themselves in a way to where they fit best and they can bond the way they're being the most stable they can be. So in carbon's example, this electron that's right here actually shifts over to that empty orbital in the p shell, and so now it's hybridized in a way to where now you have 4 different places where you form the bonds in between the carbon and the other atoms that are attached to it. So as we talk about hybridization, this is where we get into the nitty-gritty about how the electrons themselves position themselves so that way they're more stable. So it's all about being stable and the atom itself not completely disintegrating into 1,000 pieces. So the ligand repels electrons in the unhybridized d orbitals of the metal ion. So when we're talking about unhybridized, we're talking about the fact that you have the 5 energy levels, so the 5 orbitals here. All right, so and keep in mind that you can have 2 electrons per orbital. And I don't know if you guys remember Hund's rule, but that's what I'm applying here. You see, you feel 1 electron in each orbital before you double up, as you see here. So there's a total of 10 electrons in the d shell. Now, the result is the energies of the d orbitals are split, and we'll talk about what that splitting is here in a little bit. So the difference in energy depends on the complex formed and the kinds of ligands. We call this crystal field splitting energy. And then we also have strong versus weak field splitting. And we'll talk about the differences between strong and weak as we go through the next few slides. But what we are most interested in, the fact that we're getting into what is called crystal field theory. Now, you ought to remember from 151 that your S has a shape, which is a sphere. So this is S, this is P, and then D has this shape here. It's like a 4-leaf petal. So if you look at each of these drawings that you see here, each of those drawings represents a configuration with the lobes and the orbitals for each of the d electrons. And what you see here is the bottom 3 are just basically following around the x, y, and z axes, but then you go up to the top 2 and you see you got dz squared, which always reminds me of a donut, probably because it looks like a donut surrounding the nucleus. And then the x squared and y squared, where you have the x, the lobes actually on the x-axis and on the y-axis itself. So not that you have to memorize the drawings of the lobes and the orientations, but understanding how these configurations will, help to adopt the splitting that we see showing up here in the next few slides. So, and keep in mind that octahedral complexes are the most common because of the fact that the coordination number is 6. So we'll see that show up here. Now, repulsions between electron pairs and ligands and any potential electrons d orbitals results in an increase in the energy of these orbitals. That should make sense because the more repulsions, the more energy that's introduced into the environment, and the more unstable the electrons become. And so the atom itself is trying to reduce that stress by allowing this splitting to take place. So here's what a diagram of the splitting looks like. So when we talk about the splitting effect, on the left side of this picture here, you see the 5 orbitals in the D shell. But then what has to happen is that they can't exist side by side. So what they have to do is they have to split. And here's where they split. You have the 3 on the bottom and 2 on the top. And you kind of saw that in the previous slide. And then you have delta, this symbol delta here. So the size of the crystal field of splitting energy depends on the kind of ligands and their relative positions on the complex ion, as well as the kind of metal ion its oxidation state. So this is what makes the difference between a strong versus a weak field ligand. All right, we talk about ligands. We'll rank them in just a minute on the next slide or two, and you'll see how these ligands match up to each other, and it helps us to determine this gap. All right, this delta is a gap, and the larger that gap is, the less likely the electrons are going to be able to go from the bottom 3 to the top 2. So it requires a lot more energy to get up here than where you're down here. So it's just like trying to get to a second floor. All right, if you have a staircase, it makes it a lot easier. But most cases, they don't have a staircase. So if the floor is closer to the ground, the second floor is closer to the ground, it's easy to jump from the bottom to the second floor. But if you have a 20-foot tall ceiling in between you and the second floor, it makes a whole lot more difference. More people are going to be found on the first level than on the second level because not many people can achieve that higher energy state. So it's just a quick little example there, comparison. So, all right, so as we talk about the crystal field theory, we also talk about colors. And so we talk about colors because colors that we observe is really dependent on the crystal field splitting that you observe here that we're talking about. All right, so transition metal ions show many intense colors. We talked about emeralds being green because of chromium. We talked about aquamarines being blue because of iron. The color of the solutions depending on this energy state that we're talking about, and this energy state's reflected of the type of ligand. So the color wheels, I'm not going to spend much time on this, but the color wheels are important because let's just talk about copper, for example. Copper is blue. We observe a blue color, but the wavelength that's absorbed is on the opposite end. So if we see 480 nanometers, just talking about so if we see the color 480 nanometers, which is going to be right around here, it's complementary of that. So you go straight across. So the wavelength that's going to absorb is going to be right here around, what is that going to be? 620, 630. And we can see this show up within the spectrum. Now, if we were in lab this week, we would have done an experiment where we would have used an instrument that would make this graph for us, and we would be able to see what colors absorb versus what color we see with our eyes. So all this is based around the complex ion itself and the ligands that are attached. So there's no calculations, but what you do need to remember back to is the energy equations for from light. And so this was Planck's constant. This is the frequency of light, and this is wavelength. All this comes together, and that's what gives you your delta that we observe and we were talking about in the previous slide. So now this is a page that I would suggest you take a picture of. I don't think we have time to write down, but I'd say you definitely want to take a picture of and make a note of. This page is what determines the difference between a strong and a weak field ligand. You can see the list here. You have the strong field ligands here versus the weak field ligands. So do yourself a favor, taking a little note of this or take a picture of it, whichever one's easiest for you. So the strong field ligand is going to give you the largest delta. The weak field ligand is going to give you the smallest delta. And that really is going to dictate how the electrons are arranged in the orbitals as we get into those. So the next slide, I'm going to skip it, but it talks about how the electrons are arranged into those 5 orbitals in the D shell. But what I want to do is get to this slide here, because this slide really reflects on how these are 2 examples of how the electrons are arranged, and it's based off of the metal ion plus the ligands that you see here. Now, there's a lot on this slide, so let's just take it one step at a time. First thing you do is look at the metal. All right, the metal in this case is iron. All right. So iron has, and I'm only focused on the S and D electrons. So iron is in the 4th period. You need your periodic table. That's what I'm looking at right now, okay? So iron has a configuration of 1, 2, and then we got 1, 2, 3, 4, 6. So 2, 3. If we were to write out the configuration, this is the way the configuration would be set up for iron. So what we have to do first is figure out the configuration. So this is just iron that is neutral. All right. Now what we do is we look at the iron in the complex. So the iron in a complex, well, the overall complex is -4. The charge on cyanide is -1. There's 6 of those cyanides. So that gives you a total of -6. x minus 6 equals -4, so that's going to be, what, 2? It's 2 minus, yep, so that means the iron is +2 here. So when we talk about iron being +2, when we come back up here and you look at the configuration, the electrons that iron is going to lose will be these two here. So there's nothing there because it's lost. So you lose the valence before you lose your D. And so now we have 6 valence electrons in the D shell, in those D orbitals. So now we look at, so now what we do is we've got our number of electrons we need to add into this diagram here. The question now becomes, are we dealing with a low spin or a high spin complex? And that's the ligand. Low spin complexes come from strong field ligands. All right, so keep that in the back of your head. Low spin comes from strong field ligand. Now, if we look at cyanide, cyanide is a strong field ligand. So strong field ligand is going to, what it does, it pushes these two orbitals in the top here at a very high energy level. So it's to reach this. So what ends up happening is the 6 electrons fill in on the bottom for your orbitals. They can't make it to the top 2 because the gap here is too large. All right, delta is too large. So that's how we fill in the orbital diagram that we see here. The next thing we do is we figure out the magnetism. So if you don't remember this, I'm going to do a quick explanation here. So you have diamagnetic and you have paramagnetic. Di means there's 2 electrons paired together, whereas para, there's only 1 electron. So as we look at these orbitals here, we see that they're all paired up. That means that this diagram illustration represents a diamagnetic complex. So this is how we work with a strong field ligand. When we go to the next example here, we have water as our example. Water is a weak field ligand. It's neutral. The overall charge of the complex is +2. We are still working with the 6 electrons that you see here. So the electrons haven't changed, but the ligand did change. So in this example, the way it's filled in is the same way we've always learned with Hund's rule. You do 1, 2, 3, 4, 5, and then 6. So what you do with a weak field ligand is you fill all orbitals first before you double up. Now, as you look at this diagram, it's definitely it has the paramagnetism that shows up. Now, paramagnetism is what would be attracted towards a magnet. The diamagnetism is not attracted towards a magnet. So this electron configuration is what dictates of whether an element will be attracted towards a magnet or not. Now on Moodle, I have lost my paper because my internet shut off here. All right, I give you a practice set here, okay? And in this practice set, it asks for each of the following, sketch the d orbital electron levels and the distribution of d electrons among them. State the geometry, list the number of d electrons on electrons. whether they're pair or diamagnetic. So when we talk about lone electrons, going back to the PowerPoint here, when you talk about so if you look at this example on the right, there are 4 lone electrons and there's 1 paired electron. Remember, the lone electron is what makes it paramagnetic. You only need 1. So list the number of d electrons. Well, we talked about this one having 6. Both of these have 6 because the iron has a +2 charge. Now it talks about geometry. So there are 6 ligands on each of these. So that represents octahedral. All right, so that would be the geometry there is octahedral. All right, so remember octahedral or tetrahedral are the 2 more common. You do have square planar, which is a lot lesser common. We'll talk about that here shortly, but that's how you figure out the geometry. So looking at number 1 here, let's just do number 1 together so you can get an idea of how we go about solving for this. So it asks for this number of things here. So we have titanium with 6 waters. The titanium is +2. All right. First thing you do is you look up the number of electrons. So titanium has 2 s electrons and 2 d electrons. With it being +2, you're going to lose the 2 s electrons. Remember, you always lose the s electron, and then if there's remaining charge, you take away the d electrons. Okay. All right, so you have Ti. So titanium has 1, 2, 3, 4. Titanium with a +2. You lose the s, and all you have are the 2 d electrons that you see here. Now, the configuration that you're going to use bases off of the ligand, how many ligands there are. So there are 6 ligands here. So you're going to have that same octahedral configuration that we see already. So here, once we have our diagram drawn, okay, so I'm just going to box this in here. All right, so once we have our diagram drawn, now what we do is we take this configuration and we add it in. So here, water is a weak field ligand, so you're going to have a small delta, but that doesn't matter because all you have are 2 electrons. They feel in this way. So this is your diagram. Now, from this diagram, is it paramagnetic or is it diamagnetic? Well, you have 2 singles, so that means that this is paramagnetic. You've already said that it's octahedral because it has 6 ligands attached. It has 2 lone electrons. There are no paired set of electrons. So when we look down at the bottom at the answer key, we have octahedral for your geometry. You have 2 d electrons. You have 2 lone electrons, and the overall magnetism is paramagnetic because of what you've done here. So the hard part that you're going to have to do is you're going to have to figure out the charge of the metal. Then you can figure out exactly how many electrons you have left over, and then that's input here. So if you have iron, I'm just going to do this for an example here. So if you have iron, remember that iron you have 2 electrons here and you have 6. So you have 2 and you have 6 to begin with. So you lose 2 and you take away 1, that leaves you with 5. So we have none here. We have 1, 2, 3, 4, 5. So that would be the configuration of iron. Now, that does not determine the number of ligands. Typically, iron has a coordination number of 6. So when we draw our configuration here, okay? So let's say we have iron with a +3 and we have 6 waters attached to it. All right, so that's the whole complex will be +3 here. So just doing this as an example. So you have iron with a +3 charge, the complex is +3, so it's cation, has 6 ligands. The ligand is water, so the delta that you see here would be small. All right, so it'd be small. Now, so that we have 5 electrons to fill in. So we're going to have, watch what I do here. So you have 1, 2, 3, 4, 5. So there are the 5 electrons. Now before we had 6, so that we'd drawn another one on the bottom, but we don't have 6. We stopped with 5. Now, as we look at this, we see that yes, it's paramagnetic because you have 5 lone electrons. You have 5d electrons. Are there any questions with this? Does everyone understand what we're talking about? You know, what's going on here?
Yes.
Okay. So it all goes back. It hinges on the charge of the cation. So here's the charges of the cations that you may come across, and it determines by the strength of the ligand that's attached to it, whether it being strong versus weak. So all that ties into what we observe in this diagram. Now, not everything's octahedral. Tetrahedral is another type of geometry, and it has its own crystal field splitting. So now I'm just going to read the 3 points on the slide here. So because the ligands interact more strongly with the planar orbitals and the tetrahedral, their energies are raised. The reverses the order of energies compared to the octahedral geometry. Almost all tetrahedral complexes are high spin, but because of reduced metal orbital ligand interaction. So what we see is the flipping of it. So you have 2 on the bottom and 3 on top. You can see the configuration the way it's written out. Now, you would do the same exact thing as we've done before. All right, so looking at the next one here, number 2, you see how it has 4 chlorines attached to the nickel in this complex? That would be tetrahedral. You can tell tetrahedral because of the number of ligands that are attached. See 6, 6, and 6. These are octahedral because there's 6 domains. This has 4 domains, so that's tetrahedral. That's how you figure that out. So the configuration for this one would not be the same as we've been doing. It would be the opposite. You would flip it. You'd have 2 on the bottom and 3 on the top, and then everything else is done the same way. So square planar is by far the most rare, and you probably never will see it, but if you do see it, it shows up within these 4 ions here: platinum, palladium, iridium, and gold +3. The most complex splitting pattern, and almost has all low spin complexes, meaning that the electrons are going to stay in the bottom before they fill up. That's different here because it says right here that almost all tetrahedral complexes are high spin. What that means is that they're going to fill all 5 orbitals before they double up. So this is different because the energies is so much higher in these top 3. So you're going to fill the bottom ones up before you go to the next one or the next one or the next one. Again, square planar is probably the most rare of the diagrams that you're going to work with, but they form within these 4 metals here. All right, so that's a good stopping point for